Hi everyone, welcome to this talk. So we're going to be talking about a project we've been doing over the last year-ish, well, a bit longer for Wenda, I guess, formalizing some material in real algebraic geometry and sort of our experience of using the Isabelle Hall theorem prover, proof assistant to do this, and sort of what we found easier, what we found harder, and what worked. I'll start by introducing us to the subject matter, computational real algebraic geometry. So what the actual maths is. Then I'll explain a bit about Isabelle Hall, and then I'll discuss the automation that's available in Isabelle Hall, generally considered to be quite good, sort of how I found it, why it was good, where it wasn't so good. Then we'll move on to Michael, who will explain about equivalent definitions of the central object involved in our formalization, which is the real closed field, and some of the challenges associated with working with equivalent definitions of the same object. And then Wenda and I will talk about transferring results between frameworks. So we were formalizing in one theorem framework in Isabelle, and this is a difference between Isabelle and Lean, where in Isabelle the same material can be formalized again and again, or similar material can be formalized again and again in very different frameworks. And you might want to access a result from one framework in another. And so we were trying to do that, and we're going to discuss our experience of doing that. And at the end, I'll summarize. All right, so computational real algebraic geometry. So real algebraic geometry is the study of semi-algebraic subsets of the reals. So that is subsets of the reals cut out by inequalities, which is a bit different to classical algebraic geometry, where you look at stuff cut out by polynomial equalities. So, for instance, this face over here is a subset of the plane cut out by a bunch of polynomial inequalities. And so we can ask, given some polynomials, we can ask questions about the set where these polynomials are non-negative, right? So we can ask, for example, is our set non-empty? What is the dimension of our set? Or maybe you could try and compute the homology of the set. So obviously these questions have vastly different difficulties, but it turns out that there are algorithms that can decide a lot of these questions. And so that's sort of the field of computational real algebraic geometry, how we can sort of develop algorithms to compute various things. Now, so we weren't actually formalizing any of the algorithms. We were formalizing some of the preliminary material that's necessary to even sort of be able to state the algorithms. But the idea ultimately is, right, that if you can prove that some algorithms work in a proof assistant, then you can have and you can prove like a program that computes the algorithm actually does what it's supposed to. If you can verify the software, then you can in theory have reliable and fast computation for these sorts of problems. All right, so the central object in real algebraic geometry, you might think it's the reals, but it's actually something slightly more general. It is the real closed field. So a real closed field is an ordered field in which every positive element has a square root and every odd degree polynomial has a root. So that's, so the reals are a real closed field, and the real algebraic numbers also form a real closed field. And so the reason we take this more general definition will come in later, but essentially sometimes we might want to add stuff into the reals, and it's a bit like in classical algebraic geometry, where instead of just considering the complex numbers, we consider any algebraically closed field. So, a couple of points. An ordered field is a field with an order on it that respects the algebraic operations. The specific axioms aren't too important to this talk. But One very important property of real closed fields is that they have the same first order properties as the reals in the language of ordered fields. And this means that real closed fields will have, as Michael will talk about later, very many possible equivalent definitions you could take. So there's this definition here, which sort of reflects algebraic closure in some sense. It's like some of our polynomials definitely have roots, but some of them might not. And in fact, the algebraic closure of a real closed field is just like real closed field R is R adjoint I. So an ordered field can't have a square root of -1, because then is that going to be positive or negative? It squares to a negative number. But if you just add in this root, you actually get a degree 2 extension, which is an algebraic closure. So for example, the real algebraic numbers sit inside the complex algebraic numbers. Okay, so that is real closed fields. And yeah, we want to be able to compute within real closed fields. So one object we care about is the Puiseux series. So the Puiseux series over a field are their power series, but taken in fractional powers with bounded denominator and with the support bounded below as well. So these are like slightly generalization of Taylor or Laurent series, formal Taylor or Laurent series. So there's an example on the board up there. And the reason that these are really important in real algebraic geometry is the Newton-Puiseux theory, the Newton-Puiseux theorem for real closed fields, which says that if you have a real closed field and take the Puiseux series over it, then you get another real closed field. Now, you might see that in my definition of the field of Puiseux series, I've taken the indeterminate variable to be epsilon. And this is because, this is suggestive notation, in the ordering on my real closed field, this epsilon is going to be positive and it's going to be smaller than every element of my field. That's the only way I can order it. You can prove that. And so what that means is that my variable which I adjoin will essentially be an indeterminate element, an infinitesimal element. And what that means is that I can start with a real closed field like the reals and adjoin an infinitesimal element and then take the real closure. So take the smallest real closed field containing it, and that will be these Puiseux series. And that's important for several algorithms that come up in real computational real algebraic geometry, because sometimes you want to be able to compute with infinitesimals. These algorithms have a better time complexity and stuff. So it's important, if we're going to have any hope of formalizing these algorithms, to formalize real closed fields, and in particular to formalize this very fundamental theorem. However, putting infinitesimals into the picture causes a new issue. So when we're computing with algebraic numbers, we want to be able to represent them. So if we're just working with non-infinitesimal elements, like say we're working over the rationals and I have this polynomial, t cubed minus 2t squared minus t plus 1, then what I can do is I can specify a root of this polynomial by specifying the polynomial, which has finally many roots, and specifying a little interval around my root that is disjoint from little intervals around the other roots. And this is called like rational root isolation. And you can do computations where you add together numbers and multiply numbers by repeatedly refining these intervals and then adding the intervals or multiplying the endpoints, stuff like this. And that is all very well and good when you're working with non-infinitesimal elements. However, it doesn't work for infinitesimals, obviously, because they're infinitely small. So for example, the roots of this polynomial here, t times t minus epsilon, where epsilon is the indeterminate Puiseux series, whatever, those roots are rationally indistinguishable. So we need a different way to distinguish our different algebraic numbers that are different roots. And luckily we have a way. It is called Thom's lemma. So this is another one of the really fundamental theorems that we need to prove before we can even start talking about formalizing algorithms in computational real algebraic geometry. So this says that if you're in a real closed field and you have a non-zero polynomial p, then the roots of p are distinguished by the signs of the derivatives, the higher derivatives of p. So, for instance, with this thing here, with this polynomial here, the first root and the third root both have positive first derivative, and the second root has negative first derivative, so that distinguishes the second root. But then if you check the second derivatives, you see that the gradient's decreasing at the first root and the gradient's increasing at the third root. And basically, yeah, this always works. And then on the right, here's an example with the infinitesimals. You've got positive derivative in one, negative derivative at the other. Even though they're rationally indistinguishable, they still have different derivatives. So these were sort of two of the targets of our work, Thom's lemma and Puiseux series. Yeah, both very fundamental to computational real algebraic geometry and both absolutely essential to, you know, starting to write any sort of algorithms. All right, so yes, so we were formalizing in Isabelle whole. So Isabelle whole is a generic proof system based on higher order logic. So, I mean, I won't talk too much about the theoretical features of the language. In practice, the sort of two important features of Isabelle are the Isar proof language, which produces human readable proofs. Well, I'll show some proofs later, so you'll be able to judge if they're human readable. But I think they're actually quite readable once you get used to it. And also, Isabelle has the sledgehammer, which is the famous, powerful proof automation tool. Yeah. So, yeah, and so within Isabelle, there are a few different libraries for algebra that already exist. So I'm going to focus on sort of two of them. There's two main ones we're going to look at in this talk. So when you are formalizing in Isabelle, there's basically two choices you can make, at least for the algebra libraries. There's two main choices. So you can have a type class system or a locale system. So with the type class system, you annotate types with like various, I'll explain how it works in practice in the algebraic context, with various like classes such as like group, and you prove that there's an operation on your type that satisfies the group axioms. Alternatively, in the locale system, you just make local assumptions. You don't make any assumptions on the type. You just make local assumptions about the existence of some function and stuff like this. Wenda will go into more detail about the differences between the two systems and maybe their pros and cons. But I was working in a locale-based system, so that did not use type classes. And the way it worked is it defined all of its algebraic structures on a carrier set, which is a subset of your given type. So the idea of this is that it lets you work more easily with substructures. That's one of the advantages. So the difference is that, you know, if I want to define like a group G, right? So in the type class system, you end up with you know, a type tau, which is like a group, right? So you annotate it with group, and then you have your group is the entire type tau. So you have like a multiplication, which is tau to tau to tau, and then you have like an inverse, which is tau to tau, and you have an identity, which is in tau. But then in this like whole algebra locale-based system with carriers, what you have is you have this type, any type again, And instead of that, what we have is we have a carrier, which is of type set tau, which are the sets whose elements are in tau. Then you have a multiplication, which is again defined in the same way, but now your axioms are different. I'll just show one axiom. I won't write out all the axioms. I don't know if online people can see this well. So let's say we have this axiom that, you know, E times G is G. So here your axiom will be something like, for all G of type tau, G times E is G. But here you have, for all G of type tau, G is in the carrier, implies G times E is G. And so you can see that the difference between these two axioms is this extra condition here that we have. And this extra condition is an extra obligation that needs to be discharged when we prove. And as you will see on the next couple of slides, this can add up. There are obviously also disadvantages to developing algebra in a typeclass-based system that maybe Wenda will mention. Basically, it's a lot less flexible, and there's a reason that it stopped getting developed in that system. But yeah, these are sort of the differences in practice between the two systems, between the sort of proof obligations. So right, let's look at an example proof in Isabelle. So we've got an integral domain R, and we've got an irreducible polynomial P in R. And we're saying that if the degree of P is greater than 1, then P has no root in R. So I'll quickly go through the informal proof, like the LaTeX proof. So if P of X is 0 for some X in R, i.e. P has a root in R, we're going to go for a contradiction. So by the fact theorem, P is T minus X times Q for some polynomial Q. And then since the degree of P is greater than 1, the degree of Q has to be bigger than 0, and the degree of T minus X is 1. So P is a product of two polynomials of degree greater than 0. So it's a product of two things that aren't units. Contradiction, because it's not irreducible. So here is what the same proof looks like in Isabelle. So yeah, so this is where I have to try and convince you that this is human readable. So this is the Isabelle proof language. So the first thing is.
Okay.
No, it's worse. Can you just make it back to how it was? Okay. Yeah, so wait, we have this lemma. So this is giving us our locale context where we have all of our axiomatic assumptions. So this is saying we have a domain and we have a polynomial ring over our domain. So our ring is called R and our polynomial ring is called P. That's just the assumptions that are set up locally. It's called, lemma is called, irreducible implies no root. And so we assume, so again, so now we have to do this carrier checking. So in our assumptions, we have to check that f is a polynomial. If we had a type based system, we wouldn't have to check that. Type class based system, we wouldn't have to assume that. And that f is irreducible in the polynomial ring, and that its degree is bigger than 1. And we're going to show that for all elements, f of x is not 0. This is just a function that turns f into like an evaluation function. Yeah, it's like the evaluation homomorphism basically. Okay, so here's the proof. So the first thing we do is we fix x and we assume that x is in our carrier, right? So we fix a root and we go for a contradiction. So we prove by contradiction, and we have to assume that, you know, it is not the case that what we're showing is true. So the human readable proof system is a little bit inflexible. So you can't just assume the function is 0. It won't accept that as a valid proof. You have to say this.
That's not actually true. If you had left off the rule C contra and put nothing there, then it would say okay.
Would it let you?
Yeah, yeah.
Yeah, I'll try that. So we assume it's zero. It's a root, and then so the way we proceed is basically we make a claim, which is like the next line in our human proof, and then we try and use the sledgehammer to close it. So the claim is this polynomial is this is like x. This is like our t minus x in our proof. This is like our t minus x. This thing here, and then times this is like our g, but it's written out explicitly. And then yeah, we also have to prove that they're still polynomials because we have to keep checking the closure conditions. And you know, I told it to use the factor theorem, and then I think it found a proof. I think all of these proofs were found by sledgehammer. So yeah, it managed to find it, and so you see again when it was proving it, it had to check that f was really, like it had to use the fact that f was really a polynomial, and x was really an element, they're still in the carrier set, and all of this stuff. So we proved this representation using the factor theorem. Then, so I mean, at this point, you're basically done for a human. But we have like a couple of intermediate steps. I don't think it's that many more, right? So we prove that the degree of f is the sum of these degrees, which is using this lemma here, and then it has to find a few more things. And then, so therefore, both of the degrees are positive, just from these definitions. And then because they're both positive degree, they can't be units. This is what I actually had to prove. And then, therefore, we get a contradiction with irreducibility. So if you sort of ignore these lines and just focus on the hence lines, you can sort of see the structure of the human readable proof. And then once you get used to the wave notation and learn to ignore all of these sorts of conditions, you can kind of read what's going on. So this is an example. And yeah, most of the gaps here were filled in by the sledgehammer. Okay. Here's one of the lemmas we used in the last example. So let R be an integral domain, and suppose we have an invertible, a unit p, then p is constant, the degree of p is 0. And so, can you zoom back up so we have the slide focus as well? So this is something that was successfully proved by the sledgehammer. So I just put in the, okay, I mean the second one is just a restatement of the first one, so that's not very impressive. But, so I just put in that tag. So, I mean, how you would prove that is, you would say, well, suppose it was invertible, then you'd have like f times f inverse is 1. So the degree of f plus the degree of f inverse is 0, but they're both positive. So one of them has to be 0. Well, both non-negative, so one of them has to be 0. Well, so they both have to be 0 even. So in particular, the degree of p or f or whatever is 0. So I just put this in and it found all of the relevant lemmas and it strung them together into a proof, which was quite nice. This was one of the more impressive things it did. Another one of the more impressive things it did is when it proved from the axioms of an ordered field that 0 is less than 1, which is a bit fiddly, if you've ever tried to do it. It's like actually surprisingly difficult. But it's not like hard, right? Still. So these were some of the more sort of impressive jumps that the automation did. And essentially, when the automation is working well, it's sort of like, okay, of course you have to write more than you would if you were just talking to, like, explaining to a human, right, the steps, even to like a not that great undergrad. But like, you have to tell it a bit more, but like not that much more, right? And so when it's working well, you can kind of write the next line of the proof, press sledgehammer, and then wait for it. If it times out, add a little bit more detail. And it's really good with this sort of stuff where you're chaining a bunch of sort of simple claims together into one big claim. However, I'd also like to talk a little bit about the times it's not as good. So first thing is computation. So very simple lemma. If I have this degree 1 polynomial, then and I evaluate it at minus b over a, then I get 0. Now, of course, for some of the more common types, there are ways to automate stuff like this very easily. And especially in the more type class-based system, I think there's more computational automation. But there's not that much purpose-built automation. There is some. There's like a ring distributive normal form simplifier and stuff. There's not that much automation that's specific to the whole algebra library. So we were relying primarily on Sledgehammer. And it's just not very good with stuff like this. So I had to write like 8 lines, right? And most of these lines are very simple rearrangements in a field. So it's like, this is saying, you know, f of, I'll just write out one of the lines. Like, this is saying f of b over a, f0 and f1 are like the coefficients. Is the sum from k0 to 1 of like the coefficient k, times b over a to k, and then you like have to expand this out and then simplify it. And I mean this kind of stuff is very simple for us, but I found this very, very difficult to do effectively within the system and this framework, right? I should say this isn't like about Isabelle as a whole. I'm sure in other contexts there's purpose-built tools that do this, but I'm just talking in terms of the general automation. It really struggles with stuff like this. And the other thing it really struggled with, which is kind of related, is like complex objects. So this is a lemma that doesn't even take that much computation. So this says in an ordered field, if a sum of squares is 0, then every term is actually 0. And this is like true by induction, because if you have a sum of squares by induction, let's say this is true, so all of them are non-zero. So by induction, this is true. So then you're like adding on another non-negative thing. So all of them were 0, and you're adding on another non-negative thing. So you have something squared is 0, so that thing is going to be 0. So like, it's not very. It basically boils down to the fact that you're multiplying together two positive. Like you're multiplying something by itself and end up with a positive number. Like if you multiply something by itself, you can't end up with a negative number. Is what it boils down to. But because this uses this sum. The sum is defined in quite a complicated way. Well, it has to be, right? Like it's a reasonably complex object, and the automation was just quite poor. So there are these lemmas, like this lemma that says what to do when you insert something into a sum, but they weren't very effective. And one of the reasons for they weren't very easy to get to work. Like the standard proof tactics weren't very good at closing them, and Sledgehammer was like even more useless. And the reason is that basically it's because of these carrier conditions, it's because of these side conditions biting us in the ass. So you see the first 4 lines of this proof are just me specifying various closure conditions for the various things I'm working with in this proof. And that's because it can't pick them up by itself. You have to tell it to use those. Like, I mean, it struggles to even see that it has to prove those, let alone like actually be able to prove them. If you look at like what the final simplified form is, and each of them on its own is really easy for it to prove, but in the context of proving, even a slightly more complicated thing like this one here, where I'm popping one thing off a sum. It just couldn't. They just couldn't handle it. So yeah, that was another of the areas that was really painful. Anything involving sums, anything involving set comprehensions. But yeah, for the most part, the automation was pretty good. I just want to talk about these. All right. So, Matt.
I want to give some intuition behind those equivalent definition. So, fundamental theorem of algebra can be stated as any polynomial with real coefficients can be split in product of linear and quadratic polynomials. And any proof requires some topological aspect of field of real numbers. And so the standard definition real closed field is that any non-negative number have a square root and any odd polynomial has a real root is easy to see if you look at the field of real number. The second definition it's more algebraic in nature, and it states that if you have a factor ring over t squared plus 1, which is actually a field, of course, because t squared plus 1 is irreducible over ordered field, then it's algebraically closed exactly when R is real closed. The third one is basically reformulation as usual topological property for any continuous function, but we restrict only for polynomials, which we have in our inventory. And the last one is also very interesting. That basically it states that it's maximal ordered field in relation to algebraic extension. We cannot extend it algebraically and keep it ordered. And now we can look at the formalization of this in Isabelle. So we have a local ordered field with order, and the first one is direct translation. Positive colon is basically a subset of all non-negative elements of carrier R. And it says that yes, it's inside this set of squares. The second, yes, raft and carrier summation, which basically states that yes, we have this quotient this polynomial which defined by list of coefficients. The third, I think, is evident. And the fourth, it's a little bit unpleasant way to express it. And I think I can think of make it more interesting using local system, but I came with this idea only 20 minutes ago. So for now, we have this not so good-looking formulation that for any polynomial, if factor ring is actually ordered field, then polynomial should be of degree 1. And basically, it means that any algebraic extension which can be ordered should coincide with the field error. And the biggest problem is to prove implication from first to true. So basically, all other easy to formalize. And there is two possible approach. One we took, which seems more easy from informal point of view, using symmetrical polynomials, and other using Galois area. We don't need the full Galois area here. We can formalize only part of it. And actually, after some experience with symmetrical polynomials, I started to think that maybe Galois area would be easier, but it's not how it happened. And so, this lemma, which we try to prove using symmetrical polynomials, and it proves by induction. The proof is very standard. Induction by maximal power of true divided by degree of polynomial. So I'm not going into details, but it requires some result about symmetrical polynomials, which I think Wenda will be talking later. Yes, that's my part, very good.
Hello, I'm Wenda. So I'm going to talk about this symmetric polynomial. So actually the lemma that is needed for proving the equivalence definitions of RCF is this one about symmetric polynomials. It is actually a simple corollary of the fundamental theorem of symmetric polynomials. Essentially, it said, okay, for a field K, and if these x1, xd are the roots of P, and they are on some algebraic closed field of K, like C, and then if Q is a polynomial on K, and then if we evaluate Q on this X, and then the result will also be K. Note this X, they may not be from K. They can be on the algebraic closure of K, but then if Q is a symmetric polynomial, and then we evaluate Q on this element, so the result will still be on K. So this is a lemma we need. And the good thing is that some version of this lemma is already being formalized in Isabelle. As you can see, so basically this, you see there's we already have a definition of symmetric polynomials. So they said this symmetric multivariate polynomial A and Q. So they said, okay, Q is a symmetric polynomial. And also, although in this version, we don't have the a formulation of the algebraic closure, but here we say, okay, this P is equal to this, the product of this root. So this is in a form said, okay, these are the, so this Q, these roots are from an algebraic closure of the field. And then finally, this insertion is kind of means evaluation. If we evaluate Q on this set of roots, and the result is still in K. So this is more or less the lemma we need. But then, as we said, so this is a type-based formalization. And why do we say that? Is, as you can see, this dot, red dot rectangle, and it actually, so this B and A, they are type variables. We can instantiate them to concrete types like int or nat. But then, the thing come after these type variables, they are called sorts, and they are type classes. They kind of put a constraint on those type. As Artie just said, so these are type classes. And then with this constraint, it says, okay, when we instantiate these variables to concrete types, and then these concrete types need to satisfy certain assumptions, and it need to contain certain definitions. So here, these are commutative rings. So when we want to instantiate those type variables, so the instantiation need to have something like plus and the multiplications, and they also need to be commutative. They need to satisfy a certain number of axioms. So, and then with this, we say these are based on, they are type-based formalizations, because some of the reasonings, they are embedded into the type system of Isabelle. They are implicit. So they are kind of like, yeah, in the type system. And as Artie just mentioned, so there's some difference between type-based formalization and set-based formalization or locale-based formalization. But here I'll just to repeat it a little bit. So as you can see on the left is a type-based formalization. So when we say A and B are from an abelian group, and then we can have this simple lemma. So the axiom of abelian group and these closure assumptions, they are already in the type system. So the statement of this lemma is pretty concise. And then when we are instantiate this lemma to some concrete types like integers, and so we can have something like -5 plus 3 equals 3 minus 5. And this is just the statement we can use. There's no assumptions. It's pretty easy. But bad part with this formalization is that it's quite inflexible. So the carrier set is actually the whole type, and so we cannot talk about subgroup also. So on the right, it's a set-based formalization. You see it's quite verbose, and it has an explicit encoding of the carrier set. And then we also have these assumptions. This is some kind of assumptions. And so here S is the carrier set, and then with these assumptions, we explicitly encode all these axioms of Abelian group and also our carrier set S. And in addition to that, we also, for this particular lemma, we also have this X being on the carrier set and B within S, so they are the closure assumptions. And finally, we have the final statement. So the good part is, of course, it's very flexible, but the bad part is whenever we want to use this lemma, we need to discharge these closure assumptions. As Artie just showed in algebra, when the operand is quite complex, so these assumptions that we need to discharge becomes quite annoying. So what do we have in Isabelle? So it's very recent. So there's a framework called types2set, and we see the idea of this framework is kind of to have the benefit of both worlds. So we want to have the conciseness and the automation in the type-based world, and also the flexibility in the set-based world. And so it's a framework to convert a type-based formalization to a set-based one. And so the motto of this framework is prove easily and still be flexible. And so the main idea or the main thing we need to do within this framework is called relativization. So it's actually to convert this this reasoning or assumptions on a type level to an explicit statement on the set level. For example, as in the previous example, we have an implicit type-based statement saying, okay, this A is an abelian group and it satisfies certain assumptions. And then in this framework, we need to convert this into an explicit encoding of this statement, which is here AS is the carrier set, and all these operators need to satisfy these assumptions. So, and this framework is actually about converting make things explicit. And so one of the things we need to do within this framework is actually about to define a carrier to encode this explicitly. For example, over commutative semi-rings, we can have some automation to externalize those operations on commutative semi-rings. So you see this is actually a predicate that took two operators, and then it's a predicate that contains some assumptions on these two operators, which are the first one is actually plus, and then the second one is times. But then, so this predicate can be generated automatically. But then in this framework, we need to talk about the carrier set. So the thing we need to do is actually we need to manually write a locale or some predicate to imitate this automatically generate predicate, which is a little bit annoying right now. And then later we also need to relate these two encodings using the transfer package. Yeah, so we need to manually prove some lemmas like this. And here T is a binary relation, and it satisfies something, and then we can then, with this binary relation, we can relate these two encodings. Another labor we need to do in this types to set framework is also we need to compiling out the overloaded definitions. You see, as in a type-based reasoning, there are some operations, some definitions that is kind of embedded in the type system. So here we have, like, for example, the definition of power. So here is actually based on types. It has 1 and times, which means that, okay, so this type has a definition of 1, and this type has a definition, this type variable has a definition of times. So, and so this is the standard definition of power in Isabelle based on type classes. So it's quite like straightforward. But so in the types to set framework, we need to manually compile out those operators, these overloaded definitions like times and ones. So here we need to, okay, we redefine some of the previous definitions on type classes, and then we need to prove their equivalence. So basically, these are the hard part. These are the manual work we need to do in order to use this types to set system. So this system, the framework is still kind of experimental. So this manual, I think there's a recent work to reduce the labor. So these troubles I presented here may be greatly reduced in the future. But in any case, they are viable right now. So in the end, we have a locale-based formulation of the result we need from symmetric polynomials. And so here you see this K, the set, and the root. So these type variables, they does not have any constraints. They don't have type classes on top of it. So this, we can say it's a locale-based or set-based formulations. Yeah, and so this is the lemma we need. And but the proof is still in progress. Okay, that's from my part.
Yeah, thanks, Wenda. And so, yeah, I mean, so I also did a little bit of using this transfer framework. So this was in a slightly different context. So I wanted to prove Newton-Puiseux for RCFs, right? Which says that if R is a real closed field, then the Puiseux series over R form a real closed field. And now, so I mean, real closed fields aren't even available in any type-based framework that I know of. I don't think they're available anywhere right now. Well, hopefully they will be when we put them up onto the archive of formal proof soon. But right now, they're not available. But there is a formalization of Puiseux series available, where a very similar theorem called the Newton-Puiseux theorem, like the original one, is proved. And this one says, if C is an algebraically closed field, then the Puiseux series form an algebraically closed field. That is, if you take an algebraically closed field and, you know, like add, like, I don't know, like formal power series, and then take the algebraic closure, you get Puiseux series. And so, I got them the wrong way around there, but but you can see, so this one's supposed to match up to the top one. I just put the images the wrong way around. See, this one is locale-based and set-based, and this one up here is type-based. And it's actually just showing that everything with all of these sorts also has this sort. So it's adding something into the type class framework. If you're an algebraically closed field of characteristic 0, and you have a GCD on your field, that third condition shows one of the constraints of the type-based framework. So design decisions early on in the framework meant that it was not possible to naturally give fields a GCD for technical reasons. I kept thinking, oh, I can obviously fix this, and then trying and failing. And I can't remember what exactly the technical reason is now. But this is another example of the sort of inflexibility of type-based systems, that you have to add this condition, even though obviously all fields have GCDs defined in them because they're fields. The GCD is just trivial. So yeah, so these are similar theorems, and I have to sort of transfer one to the other. Well, the proofs are actually of these two theorems are actually very similar. So what I did, so basically this theorem depends on this theorem depends on a vast generalization of Hensel's lemma, which basically says that if I have like R down here and then R, the Puiseux series up here, and if I have, you know, a polynomial up here with a factorization, then I can take this and find a factorization down here of some polynomials, I don't know, for instance, with the same degree or something like this. That's basically what Hensel's lemma says. And obviously, if I now, in R, make sure that some of my... Oh, wait. Am I going this way? No, I'm going this way. No, this would be easy. Yeah, so I start the polynomials down here, and I come up with factorizations up there as well. So if I have now restrictions on what polynomials can be irreducible down here, I can create restrictions on what polynomials can be irreducible up here. And so using the proof of Newton-Puiseux, in the algebraically closed case, I was able to extract from, not like the theoretical proof, but the proof I actually had, I was able to extract a lemma which I'm going to call generalized Newton-Puiseux. It's not going to go. Hello? Hey! So this is the lemma. The details of it don't matter. But essentially, if you really, like, if you ignore the algebraically closed assumption and really see what you're proving this monstrosity of a lemma. And so what I did is I extracted that lemma. So like, for example, one corollary of this lemma is like, if all of your polynomials down here, so if you have like all polynomials of degree d dividing n reducible down here, then you have all polynomials of degree n reducible up here. So like this is like one of the things it proves. It also proves the part 2, which is even more complicated and horrible, which is needed for the positive elements have square roots of it. But yeah, like actually from generalized Newton-Puiseux to get to the real case is like not that difficult. But yeah, basically by mining the proof incredibly hard, you can sort of get a common thing to transfer. And then, so rather than now in my set space framework developing Hensel's lemma and the theory of power series, I mean, I didn't even have to prove that like Laurent series form a field. I didn't have to prove like anything like this. I just had to define my objects and prove that definitions were the same. So the set-based framework does not know what a Laurent series is. It doesn't really know anything about Puiseux series apart from this, but it knows this. And now that I've sort of got the pipeline ready, because I've done the definitions on both sides and done, as Wenda said, the manual labor to prove that the definitions all line up, compiled out all the overloaded definitions, all of this stuff, I can now sort of relatively easily transfer more results across as I need them, but only really as and when I need them. So my set-based framework knows very little, the type-based framework knows a lot, but like, so for example, here is the horrific, here are the statements of the theorem I transferred in the type-based and set-based cases. But yeah, like the point is that by using this transfer framework, you can sort of save yourself from having to develop all of the maths up to a point. If you just, yeah, once you have the pipeline ready, you can sort of transfer arbitrarily, let's say, complicated theorems across, because this is quite a complicated theorem, let's say. Right, cool. So, yeah, to summarize. So the automation sledgehammer is very effective at closing, let's say, small non-computational gaps in a proof, but it struggles with computations and more complex objects. And one of the reasons for this are these closure conditions that keep popping up that force us up to check if everything is still in the carrier set. That really messes with it. And also, it is feasible to transfer results from one framework to another so that we can make, best use of the best parts of each framework using the type set framework and the transfer package. So just before I finish, just a small note on project progress. So Newton Puiseux has been formalized for RCS, and Thom's lemma has been formalized up to equivalent definitions, and we're still working on the equivalent definition stuff because Newton Puiseux uses the polynomial roots definition, and then Thom's lemma uses the intermediate value theorem definition more naturally. So yeah, that's where we've got to, which is pretty good, but yeah, the symmetric polynomials are actually a pain. Thank you for your attention.
Thanks very much for your talk. Are there any questions from the audience?
Yes.
Yes. What is in your statement of the generalized Puiseux? What's the polynomial like? The polynomial we find? The heuristic polynomial in KT?
Oh.
Does it have a good expression in terms of the origin?
Oh, the lift. Yeah. Well, or the drop because it's contrapositive in this case.
Yes, the small p in terms of the big p.
You do a few coordinate transformations and then you do the thing in Hansel's lemma where you just reduce mod epsilon.
You just drop the epsilons.
Yeah, but you have to do a bunch of coordinate transformations first. Right, because Hansel's lemma talks about power series, and this is a Puiseux series. So yeah.
Okay, yeah, I see. So you, okay, now I see. Then you translate and then.
Yeah, exactly, yeah.
Becomes series.
And the reason you use Puiseux series is because when does Hansel's lemma fail? When you have multiple root. Puiseux series helps you beat that by letting you take nths.
Yeah. Okay.
And that's why we have this link between the polynomials.
Yeah.
That's the intuitive reason.
Okay.
There's a stack exchange question about it if you search it. So this is like in a book. I can include the source. Yeah, I mean this lemma isn't I couldn't find it anywhere. Everyone just gives a proof of this one that implies this. If you just tease out what the polynomial construction, what properties it actually has. All right. Yes.
So in the talk, you gave the type class to locale translation between the theories. Is there any point in translating from the locale to the type class?
Yeah, let's say I wanted to reason about substructures. So when I'm reasoning about substructures and maps between structures, actually all of these closure conditions are no longer superfluous. They're actually crucial.
Yep.
That's exactly what I want to reason about, stuff like that, right? And so yeah, obviously you like a framework where you could avoid them, but to some extent they're unavoidable. Because for instance, you have to show that your map is well defined. And so you can convert across, you compile out, prove your thing, and then go back.
Is this something that's done already, or is?
I mean, no. This is just something I've imagined. Do you know?
So the question is about from set based to type based.
Yeah.
Yeah, I think that is generally. So the general consensus is that development in a set based is much harder and takes more time, but it's usually much more flexible. Mm-hmm. So this direction is actually quite straightforward. You can just define the type as the carrier set. Mm-hmm. So many of the results can be directly kind of serve as a special case, as in the set based development.
Do you know any places where that's actually concretely used, for example, to reason about substructures or something?
I don't think so. Yeah, usually we know this. So from type to set is very hard. So we need this framework. But from set based to type based, it's usually very easy and quite straightforward. But I don't think there's any concrete example of that because the set based is much less developed in Isabelle.
When you're going the other way, you actually have to add a new inference rule because the assumptions about the type classes are baked in to the type. Mm-hmm. So if you you need a way to compile them out into implications, but when you're going the other way, it's fine because you already have those. You can just state those facts.
Yeah, something I really don't understand is why can you not have type classes and then have a structure which corresponds to sub-objects, which are separate?
I think this might be.
Is it because of simple types?
I think it might be a simple types thing.
Yeah.
I just wanted to comment, you're quite right that sledgehammer doesn't work so well with, say, the algebra thing. but you might find the simplifier would do work for you. So if you have the rewrite rules, because the rewrite rules are just conditional on membership in the carrier set, and then if you put the closure rules for that, you might find that it will.
Yeah, that's exactly what it was really struggling with. So Sledgehammer was completely useless, and then the simplifier was fine, but you had to spoon feed it the closure rules.
Yeah.
It wouldn't sort of seek them out, even though, like, so in this, for example, I actually have like a really good example of this with the structural issue.
Yeah, the simplifier has to begin with stuff.
Yeah, so in this case, so the simplifier did this, but it needed a bunch of closure conditions to do it. But it could also do the closure conditions. So it could do them individually, but it needs to be given the closure conditions. When the closure conditions are simple, you're fine. But when the closure condition is more complicated, it doesn't.
It probably can compose them as well, I thought, in most cases.
Yeah, so this one, I mean, maybe there's like something I'm doing wrong, but this was the worst example. And in this example, I really tried to like golf it and optimize it, and it just was not composing the closure conditions. Yes?
Just out of curiosity, in the statement with less than or equal to 0, what's SOS notation?
SOS notation.
It's just sum of squares.
Oh, okay.
Yeah, SOS stands for sum of squares.
Sounds like when the was very bad.
But yeah, the using SOS notation is just like some theorem. Oh, it's a theorem that says that like you can like rewrite. It's something about like rewriting sums of squares in terms of the formal sum notation. It's not like particularly deep. Yeah. Are there maybe any questions from the online people?
In that case, I have one last question. Did you also use multivariate polynomials in this work, or was it just sort of polynomials of one variable?
Yeah, I think in this work we use both univariate polynomial and multivariate polynomial.
Okay, because there are also two separate frameworks for that. Well, you can always define your univariate polynomial as a multivariate polynomial. Is that what you do? You also use some transfer technology to get between the predefined.
So they're defined completely differently. In fact, this formalization has two separate definitions of univariate polynomial, because we started off with one and then realized it was rubbish and then used another one, but it's fine because we have transfer. So we just transfer between them as we needed to.
Okay, yeah.
So this is how we, we're making faces at me, but this is how we do it. It's fine, like genuinely. But yeah, no, I think the multivariate and the univariate polynomials have just come up in completely separate.
Yeah, they are separate.
Actually, several entries with archival formal proof. And yes, there is a defined function which map univariate polynomial to the polynomial point variable in that particular formalization, and we need to prove that the evaluation will do the same result. So yes, it's like need to be proved.
Oh, okay. Or transferred.
Transferred, yes.
Once you have the transfer pipeline up, it is like easier to transfer more things, but it's not like you can just import the theory, because you won't have defined both sides exactly the same. But for instance, with the order of a Puiseux series, one formalization defined the order of the 0 series as 0, and like my formalization left it undefined. And then, so now you have an extra side condition. Everything has to have like non-zero conditions, right? And as soon as you add a side condition, everything goes.
Okay, then let's thank the speakers again.